Um, Hello and happy Easter. I hope you guys are having a great Sunday. Today we are looking at Introduction to Limits. And so you have a handout, and on it is the definition of limit. And it says the limit of a function. Let f be a function, and let a and l be real numbers. L is the limit of f of x as x approaches a, written like this. And so this is how they write a limit. They say the limit as x approaches a of the function f of x is equal to L. So a limit of a function is a new concept for most of you guys. And so I'm about to explain what it is. I'm going to draw a picture of the function f, and we're going to discuss what the limit is. Here's a couple of number 1 and number 2. It says these conditions must be met. Number 1, as x assumes the values closer and closer, but not equal to a on both sides of a, the corresponding value f of x gets closer and closer to a value L. The value of f of x can be made as close to L as desired by taking values of x arbitrarily close to a. Now at this point that probably means absolutely nothing to you or is confusing to you, but I'm going to draw a diagram. We're going to talk about what these mean. So here is a function right here. Let's discuss if we've got some function here, some function here. And this is going to be called f right here, okay? So let's discuss this point right here is a. This is the value of x on the x-axis called a. And let's say that if it goes up here and it hits this, and maybe this is even an open circle right here. Let's let this be an open circle. But the y value that would be right there would be L. Let's see. We'll make it a closed circle. I don't want to complicate things. But I made that point super big just to emphasize it. Really, it's just a point like any other point on here. This is the point on the curve F called when x is A, y is L. That's the point A, L. So what the limit says is that as we take x values, this is our x-axis right here, okay, and this is our y-axis, okay. So as we look at values of x closer and closer and closer and closer to a, from the left side of a, just to the left of a, as we get closer and closer, we sneak up on a, what is happening to the y values? Well, it's like you're writing the curve. So we say, what is happening here as we get closer and closer and closer to A from the left side here? The y values are right here. They're getting closer and closer and closer to this value here, L. And you say, well, what's happening if we come in from this side of X as we get closer and closer just from the positive side of A, from this side? What we're doing is we're looking at the y values. They're up here. They're getting closer and closer and closer and closer to this value, L. As we look at the limit as x goes to a from the right, it's getting closer and closer to L. So on both sides of this function, when we take x values closer and closer to a, the y values are getting closer and closer and closer to this value, L right here. So this is basically what this function is saying. As x approaches a, either from the right, a little bit bigger than a, or from the left, a little bit smaller than a, the y value approaches L. That's what the limit means. So we're going to consider a couple of other graphs. Okay, what if we have a graph that looks like this? What if we've got a graph maybe that looks like this? Let's consider 3 different graphs. Maybe we've got a graph that looks like this. Maybe this is where A is. Okay, and we've got some function here. We've got some other function, and then it's a piecewise function. So maybe we'll say right here is the value 1, and right here, this looks not quite horizontal. I want it to be horizontal. And this is the value 2. Oops. And this goes up, this is the value 3 of our y-axis. Look at my curvy y-axis, okay. And this is the value x, okay. This is one curve we're going to look at, and this is our function f. We'll call this f. Here is our function f. I'm trying to redraw this so if it doesn't look exactly the same, just forgive me. Only this time it's got like a little open circle. We'll make it snake in here like this. Okay, this is f again. It's meant to look like that. And then let's do this same function here. What if I've got a function here and it's meant to look the same? Whoops, like that, okay. Only right here we have it defined. It's got a closed circle here. Okay, all right, right here. Now, in this case, the black graph that I drew, the limit as x approaches a of the function f of x is L. The y value approaches L as x gets close to a. That's what the limit means. So that's true. It also happens to be true that f of a equals to L. That also happens to be true. However, we're going to see that is not required for a limit to exist. Okay, so right here, let's look at this right here. Let's say that we've got some value here, a. This is as x approaches a. You can look at x approaching a from the right or from the left. So these are called one-sided limits. So you can say, what is the limit as x approaches a? And you put a little negative right there, and that does not mean negative a. It means from the left side of a, of f of x. What would happen here? And what is the limit as x approaches a with the little plus sign means from the right side of f? That's what that means. Okay, so how we look at this is we say, well, as x gets close to a from the left side over here, well, where is our curve? It's all the way up here. So as we're coming from the left, we're up here, we're at 2, we're at 2, we're at 2, we're at 2, we're at 2. When we get all the way as close to a, it looks like, if we're writing the curve when we get to x is a, it looks like the y value is going to be 2. So the limit as x approaches a from the left of this side is equal to 2. All right, let's see, what is it from the right side? A little bit bigger than a. So when we're a little bit bigger than a, maybe we're at a is a plus 2, a plus 1, a plus 0.5, a plus 0.1, closer and closer and closer to a. As we sneak in up on a from the right side, it's on this curve and it's staying steady. It looks like it's going to land. It lands right here, and that's a y value of 1. So the limit as x goes to a from the right side of f of x is equal to 1. All right, let's look at this guy. Let's say that this right here is a and this right here is L. We'll just call it some real value L. The limit as x approaches a from the left of f of x in this picture, and the limit as x approaches a from the right in this picture. As x approaches a from the left, we're writing in the curve on this side of a. We're down here, we're getting closer and closer and closer. It looks like it's honing in on this value, L. That's what it looks like it's getting close to. Now, notice I'm not worried about what it's defined to be at x is a. My question when I'm looking at limit is, what does it look like it's getting close to? That's what we're answering. So what does it look like if the y value is getting close to as x gets close to a from the right side? So if we're coming in from the right side of a, we're up here on this curve, and we're getting closer and closer and closer and closer and closer to this x value a, and the y value is honing in on this same value L. That's what's happening there. And let's see. That's what's happening here. Over here, let's just take note. What is the value f of a? F of a, what is it equal to? In this instance, what is it defined to be? Well, here's the closed circle, so it's defined to be 1. All right, fine. Over here, what is f of a defined to be? Well, it's an open circle, and it's not defined anywhere. Right here, f of a is undefined. It's undefined in that instance. Okay, over here, let's see what's going on here. If this is a, and this is L, and let's see, what do we want to call this? Let's call this some other value up here. Let's call this M. All right, the limit as x approaches a from the left of f of x, the limit as x approaches a from the right of f of x, as x approaches a from the left. As x approaches a from the left on this side, we're coming in, we're getting closer and closer to this point. It looks like it's headed to this y value, which is called L. From the right, okay, we're on this side, we're writing in the curve from here. It's like you're writing it in, so you get closer and closer and closer and closer to x is a. It looks like it's heading to the same point. So the limiting value as x gets close to a is L. However, what is f of A in this instance? It is defined. The closed circle is up here. It's defined as M. Okay, so let's hang on to what it's defined to be. Just leave that alone. We'll leave that alone. Just notice that that's totally separate from what the limit is. Doesn't have any bearing on what the limit is. When you're saying what is it defined to be, you're looking at where it's closed circle. When you're saying what's the limiting, you're saying what is it getting close to. Now, for a limit to exist, if you look at the top part of this definition on the sheet, it says, as x assumes values closer and closer to A on both sides of A. Here's for a limit to exist, the left-sided limit from the left and the right-sided limit from the right, they have to be the same number. So right here, as I get close to A from the left and from the right, I am not agreeing. I'm totally missing. See, from the left it was 2, from the right it was 1. These are not the same number. So this is what we conclude here. The limit, let me get a brighter marker. The limit as x approaches A of f of x does not exist. And it does not exist because these two numbers do not agree. Was the function defined at A? It surely was, but that did not matter. The limit did not exist. Okay, those are separate issues. Right here, the limit as x approaches A of f of x. From the left it was L, from the right it was L, and so it agreed. So we'd say the limit as x approaches A of f of x is L. Was A defined? Was x equals to A defined? Was not even defined, but that didn't matter. We still have a limit. Right here, the limit as x approaches A from the left is L, from the right is also L, so they agree. So the limit as x approaches A of f of x is equal to L, okay? What was A defined to be in this instance? It was defined to be a different value, M. It wasn't L, it wasn't defined to be L, it was defined to be M, but yet the limit exists. So we've seen 3 cases where the limit exists, but where it's defined is different, right here. This top curve in the black. The limit as x approaches A from the left and the right are L, so the limit exists, and it's also defined to be L at A, okay? The limit as x approaches A from the left and the right is also L, but is it even defined here? Not even defined. The limit as x approaches A from the left and the right agree, it's L, but what is it defined to be? It's defined to be M, not L. So all of these have the same limit. It approaches, it is L. However, they're defined differently. When does the limit not exist? When it does not agree from the left and the right. That's when it doesn't agree. Okay, so that is an introduction to limits. So what you're asking is, what does it look like when it gets close to? I want us to re-look at asymptotes. This is an interesting discussion. So let's look at asymptotes. We have looked at horizontal asymptotes and vertical asymptotes. And so on your sheet there, I have the definition of how they're really defined. And I didn't put it to you this way when we started talking about it, but let's look at what asymptotes are. A horizontal asymptote says that as the limit of x approaches a very big number, like infinity, or as the limit of x approaches a very big number like negative infinity, then the y value gets very close to the same horizontal line. So this is what a horizontal asymptote is. Horizontal asymptotes are defined like this. The limit as x approaches positive infinity of f of x, it equals to some value c. So basically, y is equal to c when x is very, very big and positive. Or the limit as x approaches negative infinity of f of x equals to c, y equals to c is, in both of these cases, this defines a horizontal asymptote. Let's look at a picture of 1 over x. Whoops. 1 over x looks like this. Or, well, this is 1 over x. As we get closer and closer, as x gets further and further down the x-axis, it's getting closer and closer to the x-axis, or y equals to 0 is a horizontal asymptote. or as x gets big and negative, y equals to 0 is the horizontal asymptote. This is the picture, and this is what the language is in limit talk. What if I change this slightly? 1 over x plus 3. This is the basic graph, 1 over x, but it's being shifted to the left, 3. So let's shift it to the left, 3. 1, 2, 3. So this is my new xy axis, right? So that means I'm going to have a picture that looks like this. Okay, that's fine. What is my horizontal asymptote? It's still 0. As x gets to positive infinity, it's going to 0, and negative infinity, it's going to 0. So we would say the limit as x goes, and you could even draw it like this, plus or minus infinity of 1 over x plus 3 is equal to 0. And that means that y equals to 0 is a horizontal asymptote. Let's do one other thing with this. What if we say 1 over x plus 2? Okay, this is the basic graph, 1 over x, but it shifted up 2. So we go up 2. So this will be my new x-axis. Y-axis, it's going to look like this. Okay, all right. So what's happening here, as x gets very, very big and positive, it's getting close to the line y equals to 2. That's what it's getting close to. So we would say that the limit as x approaches positive infinity, and we could also say the same thing for negative infinity. So we could say plus or minus infinity of f of 1 over x plus 2 equals to the value 2. This statement right here is also saying that y equals to 2 is a horizontal asymptote. Now let's look at what the vertical asymptote definition is. Vertical asymptote says as x gets close to a value, so that was horizontal. Let's look at vertical. Vertical asymptotes say the limit as x gets close to some value. What did they use? They used h. Okay, we'll say h from the right. It goes to infinity, either plus or minus infinity. And the limit as x goes to h from the left goes to plus or minus infinity. If any one of these things is happening, that's enough to say that there's a vertical asymptote. So I'm going to switch to red because I think the green, I can hardly see it. So, or blue. Let me go to blue. So, oh no, I just did blue. Let me do red. What did I do with all my colors? Here it is. That's it. Let's look at these two graphs. Okay, ready? The limit, let's consider this. What is the limit as x approaches negative 3 from the left of 1 over x plus 3? Okay, this is negative 1, negative 2, and this is negative 3. Okay. As x gets close to negative 3 from the left, here we are on the left, we are going to down as far as we can go. We're going to negative infinity. This right here, this information right here is enough for me to say that x equals to negative 3 is a vertical asymptote. Separately, what if this is enough to say this, but also we have another thing going on that would make us say that. The limit, let's look at the limit as x approaches negative 3 from the right. So here's negative 3, so we're coming in from the right. It's shooting up to positive infinity. This statement right here, if any one of these things is happening, is enough for me to say x is negative 3 is a vertical asymptote. Over here, where's the vertical asymptote? Well, as we get closer and closer, the limit as x approaches 0 from the right, let's see, from the right, we're over here, our function's going to positive infinity. This is enough to say x equals to 0 is a vertical asymptote. And the limit as x goes to 0 from the left, it's shooting down to negative infinity. Basically, functions totally freak out when you try to make them divide by 0, and that's where you get a vertical asymptote. This statement right here is enough to say x equals to 0 is a vertical asymptote. Okay, so that is, I want to do one other thing with you guys. This kind of have, but we're going to get the other worksheet that I have posted under there. So the other worksheet is about the kind of the notation or the language of limits. If you look at number 1, it says, as n approaches infinity, v of n approaches 4/3 pi r cubed. How could we write that in limit talk like this? Number 1, we'd say the limit as n approaches infinity of v of n is equal to 4/3 pi r cubed. That's how we would do the first one. The second one, as n approaches infinity, a sub n approaches this expression. So for number 2, we'd say the limit as n approaches infinity of a sub n is equal to ax cubed plus bx squared plus cx plus d. That's how we would do number 2. Number 3 says, as t approaches negative infinity, e to the t plus 2 approaches 0. Okay, so number 3 we would say the limit as t approaches negative infinity of e to the t plus 2 equals to 0. Number 4, as t approaches negative infinity, or the limit as t approaches negative infinity of the sine of g of t, of the sine of g of t, this y approaches 1. Okay. What about number 5? As x increases without bound. That is another way to say as it goes to positive infinity or negative, increases without bound goes to positive infinity. So number 5, you can say the limit as x increases without bound as it goes to positive infinity of the cosine of 1 over x is equal to, it approaches 1, equals to 1. That's the limit. Number 6, as x decreases without bound, that's a way of saying as x goes to negative infinity, the limit as x goes to negative infinity of 5x minus 3 over 2x squared minus x minus 1 approaches what? It approaches 5/2. So that's 1, 2, 3, 4, 5, 6 on the purple sheet, or the other handout about the language. And we're going to deal with number 7 in part 2 of Introduction to Limits. So we're about to do that one.